Hello everyone. Uh, First of all, I'm very much feeling great for having this opportunity uh, to give my final presentation in the course ADTA 5550. So uh, the final project is the title is CNN on CIFAR 10 data. So uh, here's the presenter. So my name is UdaySashankKanapala of student ID 116444787, and today's date is Monday, March 4th, 6:30 a.m. So let's go into the presentation. Let's dive more. So title: Building a Convolutional Neural Network CNN on the CIFAR 10 dataset. So regarding coming to the introduction, so in today's presentation, we'll be diving into the realm of deep learning by exploring the construction of convolutional neural network (CNN) on the CIFAR 10 dataset. As data continues to hold immense value in today's world, harnessing the power of deep learning is crucial for extracting meaningful insights. So, meaningful insights helps us a lot in developing the future goal. So, the CIFAR 10 dataset, known for its rich features and ample size, serves as an excellent playground for deep learning analysis. So, TensorFlow use. Yes, in this project, we opted for TensorFlow as our primary framework. It's worth noting that we exclusively utilize TensorFlow without incorporating the Keras library or its constituent APIs. This decision was made to foster a comprehensive understanding of TensorFlow's capabilities and to delve deeper into its intricacies. So, image data search. Image data search. So, is the image data search. So, while coming regarding the image data search, our journey began with an exploration of a food image dataset. There you see in this picture, you see the food evaluation dataset. The picture worth 1,000 words. So a food image dataset comprising 2,500 food and non-food items categorized here into 11 broad classes. This dataset provided a fertile ground for classification analysis due to its pre-processed nature and well-defined features. You can access this. See, you see the data of 2,500 food and other 2,500 non-food aspects that make the data a perfect candidate for classification analysis. You see, there are uh, 16,643 images with 11 broad categories of data include rice, eggs, bread, dairy, meat, noodle, pasta, dessert, food, soups, whatnot, vegetables, seafoods, etc. So I choose the data due to its pre-processed nature with files correctly labeled and features perfectly defined. So as we see, uh, the items categorized into 11 broad classes. This dataset provided a fertile ground of classification. You see, this dataset provided a fertile uh, ground of classification analysis due to its pre-processed nature and well-defined features. You can access this dataset via you see, I provided the link at the bottom of this. You can access this dataset over here from here. So we can dive into the data and so we get to see all these images and everything through the link provided out there. So the image data I choose to present regarding food suits this explanation. I feel it explains a good detail, and as food is our day-to-day consumption, so we feel it will be so easily understood because as it's part of our life. So let's dive into the, you see, CIFAR 10 data set. CIFAR 10 data set. Here you go. CIFAR 10 data set. So we acquired the CIFAR 10 dataset from module materials on Canvas, leveraging the Google Cloud Platform (GCP). We initiated a virtual machine. You see, the data to use to the implementation of this paper was downloaded from module materials and in GCP platform, that which I has explained clearly in the text. The virtual machine. We initiated a virtual machine VM and seamlessly uploaded the dataset files following meticulous organization into a dedicated subfolder. You see the folders over here in the picture, and the dataset was primed and ready for analysis. So the unzipped files were then uploaded one by one into the virtual machine. On completion of the data subfolder of all the folders, a new subfolder was created and named CIFAR underscore 10 underscore data. This is the last step of the quest, was to move the files from home directly to newly created subfolder. You see the CIFAR or here the is a sub. Uh, I have acquired this CIFAR 10 dataset from the module materials as provided by the professor in the Canvas. We initiated simply a virtual machine and seamlessly uploaded dataset files following meticulous organization into a dedicated subfolder. The dataset was primed and ready for analysis. Yeah, the dataset is ready for analysis now. So we can do various analysis through the dataset and accomplish our goals. Okay, so uh, let's jump into the CNN. You see, the CNN on CIFAR 10. You see, the next step that I was built was CNN using the newly uploaded CFR10 image data previously. The Python template to help import the files was downloaded from Canvas and uploaded to a running Jupyter session in the virtual machine. So, following the meticulous organization into a dedicated subfolder, the data set previously was primed and ready for analysis in the data CFR10 dataset. But while regarding the CNN architecture, you see the design after CNN data, I have followed the following step to build a CNN using the newly uploaded CIFAR10 image data. The Python template to help the import files was downloaded from Canvas. So we have uploaded into Jupyter session in the virtual machine. So while regarding the CNN architecture, the design, the design of the CNN featured the following architectural shape. Our CNN architecture boasted a structured design comprising. You see the design here. The design. Let me highlight uh, the design. Uh, and moreover, the convolution layers with RELU activation, pooling two pooling layers that condense input from each convolution matrix. The pooling layers are activation as well. I fully one fully connected layer, one dropout layer, and an output layer with shape 10. So here in the CNN architecture, it's boasted structured design comprising convolutional layers with rectified linear unit uh, activation, pooling layers with rectified linear unit activation. So those two steps that I mentioned, we need two of them. So from here, one fully connected layer, one dropout layer, and an output layer with shape of 10 units. This is meticulously crafted. You see here the design is visualized below. Here you can find it. So one picture is worth 1,000 words. You can find from here. Uh, and mm, Architecture product robust framework. You observe this robust framework in this picture. The input, you see the dimensions, each and everything. We get a clear idea from it. And there's N1 channels and N1 12 into 12, 12 by 12 N1 and two channels, 8 by 8 and 2, and 4 by 4 and 2, the flat end and 2, the 4 by 4 is flat end. And you see the dropout, the output is 9, the max, the fully connected neural network. You observe the max pooling, you see the pooling. Uh, and you see the results. The model was trained on over 5,000 steps and evaluation done after every 100 iterations. At step 4,900, you see, for after every 100 iterations, you see 5,000 steps. The step 4,900, you see the step 4,900 step. The model showed an accuracy of 69.2%. You see the accuracy rate. What's that? The accuracy rate is 69.2%. Let me. So you see, so in 5,000 steps, in the step 4,900, the model showed an accuracy of 69.2%. So one step worth the 4,000. On step 4,900, accuracy is 0.692. Is represented in the picture here, and is the training graph. The results after see after the rigorous training over 5,000 steps, and our model achieved an impressive accuracy of 69.2%. Notably, evaluation at step 4,900 demonstrated consistent improvement over time. So visualizing the training graph here, you see the graph listed here showcase the clear trajectory. You observe the trajectory of incremental accuracy enhancement with prolonged training. You see the training prolonged until 5,000 steps, underscoring the effectiveness of our approach. So better accuracy was inevitable with more time. So if the time increase, we get more accuracy. There's a trajectory increment over here. So now let's compare the CNN performance. So CNN performance. Let me highlight it. Comparing the CNN performance after the results. So it's time to compare the CNN performance. So it's very crucial. Comparing the CNN performance, it plays an pivotal role, you know. So we get to understand the things more deeply when comparing. So when comparing the performance for CNN on the CIFAR 10 dataset, mm, with that on the MNIST dataset, notable differences emerge. You see the difference emerged here. You see the difference in this picture from the left side of the half of the page is different from the right side. The green color trajectory, you and you see the difference occurs emerge, and Sifferton exhibited lower accuracy. You see the accuracy here, the Sifferton exhibited lower accuracy, and it's shaky. Uh, on the same CNN architecture as evidenced by a plot comparison. The complex nature and larger size of Sifferton pose unique challenges, thereby influencing the performance of our model. So, a struggling nature in extracting features that empower it to deliver quality on a new data. The low results of CIFAR 10 data also point to huge and complex nature of the data set. Is quite the MNIST is quite smaller as compared to CFAR 10. So let's improve the CNN performance. So improving the CNN performance. To you see the picture here, the progress plot shows about 70% accuracies as the number of steps near 5,000. In the step 5,000, there's a 70% accuracies. This improvement can be attributed to the layer added onto the model. So on the existing architecture, uh, to augment the performance of our CNN model, we implemented a strategic modification by incorporating an additional convolutional layer. This adjustment here yielded a noteworthy improvement, boosting the accuracy to 70.1%. The progress plot, you see the progress plot when you observe at the steps 5000, vividly depicted the consistent accuracy gains, particularly evident near the 5000 step mark. You see, vividly see near 5000, near 5000 step mark, we observe vividly of 70.1% progress. So, uh, yeah. uh, let's uh, let's come to conclusion once and let's revise the key points again. So, in conclusion, my exploration into statistical modeling or coupled with deep learning reaffirms the potent capabilities of this approach in tackling diverse datasets. It's essential to recognize that building effective models necessitates necessitates tailored methodologies and continual refinement. Our journey underscores the iterative nature of achieving optimal results and highlights the intricacies of model building. So, what I'm trying to say from the top, you see, let's go to the so the final project CNN on CIFAR 10 data and his introduction data is uh, you see uh, so data is the new gold and leverage deep learning is key to extracting insights. Today we delve into building convolutional CNN network. This data is renowned for its robust features and size, making it an ideal candidate for deep learning analysis. So we use the TensorFlow usage as and for this project, notably no Keras library was being taken part here. So the image data set, I take the food image data set data. So we are recapping from top to bottom. The final project was on food image data. You see, for this project, I initially explored food image data set consisting comprising 2,500 food and no food aspects. This data set facilitated different things we observed, we got to know. So we obtained a CIFAR 10 data set. Okay, here we come the data set and from through GCP and Canvas, I got it from there. Uh, so OCN, the design, when you observe the design, so this is the comes to the main part. This is very two CNN convolution layers with the C with the RLU activation. You got to see over there. Uh, so rectified linear unit activation and pooling layers with RLU. And two of those each. You need two convolutional layers with rectified linear unit, two pooling layers with rectified linear unit activation, one fully connected layer, one dropout layer, an output layer with shape of 10 units. So you see the diagram, when it comes to the diagram, you got to know the clear, better understanding. And the result at the step 5000, you got after every 100 iterations. At step 4900, all the steps of 5000, we showed an accuracy of 69.2%. So the graph over here at step 4900, we get to accuracy of 69.2%. But at the step after comparing the CNN performance, so the fully connected layer, you see, after comparing it, you get to know Uh, it improved almost. Yeah, if the left side is different from the right side, as I said, so the quite smaller and compared to CFOT 10. You see, MI, MNIST is quite smaller as compared to CFOT 10 graph. So improving the performance. So when comparing the performance of our CNN on the CIFAR 10 dataset with that the MNST dataset, notable differences emerged. CIFAR 10 exhibited lower accuracy on the same CNN architecture. You see the data, the two pictures, uh, thereby influencing the performance of our model. So the crucial step is improving the CNN performance on the existing. You see, it's very mandatory or crucial to improve the data set. Uh, so the performance of our CNN model, we implemented a strategic modification by incorporating an additional convolution layer. By additional layer, this adjustment, you see, this adjustment by incorporating this additional layer, this adjustment improves the accuracy from 69.22, you see, the 70.1%, 70.1% at the step 5000 mark. So, uh, conclusion. In conclusion, my exploration, you see, into statistical modeling, coupled with deep learning, reaffirms the potent capabilities of this approach, but also opens a path to sustainable development of real world solutions to rather complex problems. From this analysis, I have learned the job of model building is complex and requires tailoring a model to specific data. Continual improvement of model is also key to achieving better modeling results. So, as per my conclusion, that's my conclusion for the project of ATT 5550. So here at bottom last, I provided references. Uh, See, you can access all the data sets and images from over here and the references that I have used linked below. So let me link the link for you. There you go. So lastly, here's the references throughout my presentation. Feel free to explore these sources for further insights and information. Uh, so so uh, now, so I conclude my final presentation on CIFAR 10 data, CNN on CIFAR 10 data. So thank you, everyone, each and everyone who watches this video, spending your time uh, on my research and on my project work that I've done. I'm grateful to you. And one more time, thank you, Professor, for giving me such an opportunity to improve my skills. And I enjoyed throughout the coursework, and the presentation is at the peak of it. Thank you. So, thank you, UdaySashankKanapala. This is UdaySashankKanapala as the presenter, and hope you enjoyed watching it. Thank you. Thank you so much.